In this lecture, we will continue our introduction of complex variables by discussing the complex plane and complex conjugates. So we define a complex number as a real number plus a real number times I. So let's write the complex number z as x plus iy. And we're going to interpret this complex number as an ordered pair where the coordinates are the real part and the imaginary part of z. So the complex number z equals x plus iy can be interpreted as a point or ordered pair x comma y, and then we'll use our knowledge of the Cartesian coordinate system to identify this on a plane which we call the complex plane. Or we can call it the z-plane. So we have two axes, and the horizontal axis is identified as the real axis, and the vertical axis is called the imaginary axis. So we put the imaginary numbers iy on the imaginary axis. So given a complex number z, x plus iy, we identify with the point xy in the complex plane. So some other examples, like the complex number I, the pure imaginary complex number I, would be identified with the point 0, 1 in the complex plane. So this would be the point I on the complex plane. And any real number x would be displayed as a point x0 on the real axis, and any pure imaginary number iy would be displayed on the imaginary axis by the point 0y. So we'll see that visualizing the complex numbers in the complex plane is going to be very useful throughout this semester, especially when we get to graphs of complex valued functions. So it is also natural to associate any non-zero complex number z, which is x plus iy, with the directed line segment or vector from the origin to the point xy. In the complex plane. So for example, if I had complex plane here, and then let's represent some complex numbers like the complex number 1 plus 3i, will be represented by the point 1, 3. And then we can use this vector to represent this complex number as well. So if I wanted to add the complex number 3 plus 2i, let me represent 3 plus 2i as a point. So the point 3 comma 2. And let's look at its vector. Then if I wanted to add these complex numbers, you see we'll get 4 plus 5i, and if I plot the point 4 comma 5 on the z-plane, we'll end up about right there. And we see that if I take the vector 1 plus 3i and add it to the vector 3 plus 2i, we get exactly the vector 4 plus 5i. So it works the same way if I use the other side. So we see that vector addition is a good representation for the addition law in the complex numbers. So this vector interpretation of the complex numbers is useful for extending the concept of absolute value from the real numbers to the complex numbers. So we define the modulus, or absolute value of a complex number, z, which is x plus iy, to be the non-negative number non-negative real number denoted by the usual notation of bars around the complex number z, and defined by the absolute value of z equals the square root of x squared plus y squared. The absolute value of z, or the modulus of z, is equal to the distance from the origin to the point xy in the z-plane. So if we have a point xy in the z-plane, then the length of this vector from the origin to the point xy is equal to the modulus of z, or absolute value of z. So, and if you just use the Pythagorean theorem, we get this formula for the absolute value of z. So for example, if I want to take the modulus of 4 plus 3i, that would equal the square root of 4 squared plus 3 squared, which is the square root of 25, or 5. So a couple of notes. To say that z1 is less than z2, this is meaningless for general complex numbers unless both complex numbers are real. So the complex numbers is not an ordered set. It doesn't make any sense to say that z1 is less than z2 in general, but we can say that the absolute value, or the modulus of z1, is less than the absolute value of z2. This would mean geometrically that z1 is closer to the origin than z2. So now with the modulus defined, we can define the distance between two complex numbers. So the distance between the complex number z1, which is x1 plus I y1, and z2, which is x2 plus I y2. This is given by the modulus of z1 minus z2, which looks like square root of the quantity x1 minus x2 squared plus the quantity y2 minus y1 squared. So with this notation, we can also define a circle in the complex plane. So the circle in the complex plane with center z0 and radius capital R is the set of all points in the complex plane that are distance r from z0. So we can write it by the equation modulus of z minus z0 equals r. So any complex number z that satisfies this equation will be a distance r from z0 and therefore be on the circle. So for example, if we looked at the expression absolute value of z plus 1 minus 3i equals 2, we can look at this as an equation of a circle. If I rewrite this expression as z minus the quantity negative 1 plus 3i equals 2, then we see that this is the circle centered at negative 1 plus 3i with radius 2. So quick sketch, if I write the point negative 1 plus 3i as a point on the complex plane, it would be about right here, identified as the point 1, 3, and then the circle has radius 2, so it looks something like this. Now we're going to look at some useful inequalities. So if we start out with z equal to x plus I y, we have the modulus of z equal to square root of x squared plus y squared. And then using our notation for the real part of z and the imaginary part of c, we can write absolute value of z squared equal to x squared plus y squared, and then substituting for where x is the real part of z, we get the expression absolute value of z squared equals the real part of z squared plus the imaginary part of z squared. And from this we can obtain some useful inequalities. We see that the real part of z will be less than or equal to the absolute value of the real part of z. So we note that the real part of z is just a real number, and so the modulus of a real number is exactly the absolute value of that real number. So the modulus of a real number just reduces to absolute values. So the real part of z is less than or equal to the modulus of the real part of z, and by the previous expression we see that the real part of z must be less than or equal to the absolute value of z. So if you think about it in terms of components, x is less than absolute value of x, which is less than or equal to the square root of x squared plus y squared. And then likewise we have the inequality that says the imaginary part of z will be less than or equal to the absolute value of the imaginary part of z, which will be less than or equal to the absolute value of z. So another useful inequality is the triangle inequality. Which states that the lengths of any two sides of a triangle is greater than the length of the third side. In other words, the shortest distance between 2 points in the plane is a straight line. So we have the triangle quantity for complex numbers. The absolute value of z1 plus z2 is less than or equal to the absolute value of z1 plus the absolute value of z2. And by using mathematical induction, it can be shown that the triangle inequality extends to sums with any finite number of terms. So in other words, the modulus of z1 plus z2 plus all the way up to zn will be less than or equal to absolute value of z1 plus the absolute value of z2 plus all the way out to the absolute value of zn. We will prove the triangle inequality in a few minutes after we define complex conjugates. So I mentioned this in an earlier lecture that the complex conjugate of z equal to x plus iy is denoted by z with a line over it, read z bar. We define this as x minus iy. So if you just change the sign in between the real and imaginary parts, then you get the complex conjugate z bar. So the number z bar is represented by the point x negative y in the complex plane, and we see that this is a reflection of xy across the real axis. So if I had a point z, which is x plus iy, then the conjugate of z would be the reflection across the real axis. So there's z bar identified with the point x negative y. A couple other notes. We see that the conjugate of z conjugate, I would get back to z. If we take the reflection again, you can see you get back to z. And further, the distance from z to the origin is the same as the distance from the conjugate of z to the origin. So we see that the absolute value or modulus of z equals the modulus of z bar. So now we'll talk about some facts about conjugates. And most of these facts can be proved quite easily by writing z1, z2 as components like x1 plus iy1. So the first fact that we're going to look at is that if I want to take the conjugate of a sum z1 plus z2, then that is equal to the conjugate of z1 plus the conjugate of z2. Secondly, if I have a difference, I want to take the conjugate of a difference, I can break that up as the conjugate of z1 minus the conjugate of z2. Next, the conjugate of a product is the product of the conjugates, z1 conjugate times z2 conjugate. And likewise for division, if I want to take the conjugate of a fraction z1 over z2, that is equal to the conjugate of z1 divided by the conjugate of z2. Next, fact 5, I can write the real part of z as z plus z bar divided by 2. So see, if we have z plus z bar, the iy and the minus iy will cancel out, so I end up with 2x. And so if I divide by 2, I get back to the real part of z. And similarly, the imaginary part of z can be written as z minus z bar divided by 2i. For 7, z times z bar will give the modulus of z squared. This fact is equivalent to the fact that 1 over z can be written as z bar over the modulus of z squared. And you see that that matches up with our notation for 1 over z from the first lecture. The last two facts don't have conjugates in them, but I'll use conjugates to prove these facts, that the absolute value of z1 times z2 is equal to the absolute value of z1 times the absolute value of z2. And for division, this works as well. the absolute value of z1 over z2 is equal to the absolute value of z1 divided by the absolute value of z2. And this works for non-zero z2. So facts 9 and 10 don't involve conjugates, but we can use conjugates to prove facts 9 and 10 very easily. So let's do a couple of proofs. Let's look at the proof of fact 1, that the conjugate of a sum is the sum of the conjugates. So for this, I'm going to write z1 and z2 as components x1 plus iy1 and x2 plus iy2. So z1 plus z2, I could write that as x1 plus x2 plus the quantity y1 plus y2 times I. And so then I'm taking the conjugate of this expression. So we define the conjugate of this expression to be x1 plus x2 minus the quantity y1 plus y2 times I. And when I distribute the minus I get x1 plus x2 minus y1I minus y2I, and I can rearrange this as x1 minus y1I plus x2 minus y2I, which is z1 conjugate plus z2 conjugate. So facts 1 through 4 have similar proofs, so I'm going to omit those. Let's look at fact number 9, which states that the modulus of z1 times z2 is equal to the modulus of z1 times the modulus of z2. So I'm actually going to start with the quantity absolute value of z1, z2 squared. Then using fact 7, I can rewrite this as z1, z2 times the conjugate of z1, z2. So that was property 7 I just used. And then the conjugate of a product is the product of the conjugates. That's fact 3. So I'm going to write this as z1, z2 times z1 conjugate times z2 conjugate. And then, since complex numbers are commutative, I can write this as z1 conjugate times z2 conjugate. And then using fact 7 again, I can put this back as the modulus of z1 squared times the modulus of z2 squared. Then using the commutative property of real numbers, I can write this as modulus of z1 times the modulus of z2, the quantity squared. So now take square roots, and we're not taking square roots of negative numbers because we assume that the modulus is never negative. So fact number 10 can be proved similarly. So I'm going to use these facts about conjugates to prove the triangle inequality. And the triangle inequality is useful for finding upper bounds of quantities. Consider the quantity absolute value of z cubed plus 3z squared minus 2z plus 1. We can find an upper bound for this quantity and where z is inside the circle centered at the origin with radius 2. So this will be useful in later proofs involving these types of expressions. So we're going to try to find an upper bound for this quantity. Well, if z is inside the circle with radius 2, then we know that the modulus of z will be less than 2. By property 9 and the triangle inequality, we have that the absolute value of z cubed plus 3z squared minus 2z plus 1 will be less than or equal to the absolute value of each term, property 9 says the absolute value of z cubed is just the absolute value of z to the third power, and then the absolute value of 3z squared will then be the absolute value of 3, which is 3, times the absolute value of z squared, plus the absolute value of negative 2, which is 2, times the absolute value of z, plus the absolute value of 1. And then now using the fact that absolute value of z is less than 2, we get that the absolute value of z cubed is less than 2 cubed, and then so on. So plus 3 times 2 squared plus 2 times 2 plus 1, and we get an upper bound for this expression of 25. So we see that the triangle inequality is useful for finding upper bounds of absolute values of complex quantities. Now we'll prove the triangle inequality. Which states that the absolute value of z1 plus z2 is less than or equal to the absolute value of z1 plus the absolute value of z2. So just like in a previous proof, I'm actually going to start with the quantity on the left hand side squared. So the absolute value of z1 plus z2 squared. And then by fact 7, I can write this as z1 plus z2, the quantity, times z1 plus z2, the quantity conjugate. And then by property 1, I'm going to break this up as z1 plus z2 times the quantity z1 conjugate plus z2 conjugate. I'm just going to use the FOIL method to multiply this out. This is z1 bar plus z1 z2 bar plus z2 z1 bar plus z2 z2 bar. Property 7 again, we see that we can rewrite z1 bar as the absolute value of z1 squared. And I'm going to rewrite z2 z1 bar as the conjugate of z1 z2 bar. And by property 7 again, I'm going to write z2 bar as the absolute value of z2 squared. So if you look at the middle two terms, I have a term plus its conjugate, z1 z2 bar plus the conjugate of z1 z2 bar. Well, when I add a complex number with its conjugate, you'll obtain twice the real part of that complex number. So this is essentially property 5. So I have the absolute value of z1 squared plus twice the real part of the real number z1 z2 bar plus absolute value of z2 squared. Well, then I'm going to use the fact that the real part of a complex number is less than or equal to the modulus of a complex number. So absolute value of z1 squared plus 2 times absolute value of z1 z2 bar plus z2 bar squared is going to be greater than or equal to the previous quantity. But I can break up the absolute value of z1 z2 bar as the absolute value of z1 times the absolute value of z2 bar, but noting that the absolute value of z2 bar is the same as the absolute value of z2, when we get absolute value of z1 squared plus 2 times absolute value of z1 times the absolute value of z2 plus the absolute value of z2 squared. And this expression factors as absolute value of z1 plus the absolute value of z2, the quantity squared. So again, we take the square roots, to obtain the triangle inequality. Now let's look at a couple of corollaries to the triangle inequality. If we replace z2 with negative z2, we obtain the following result, that the absolute value of z1 minus z2 will be less than or equal to the absolute value of z1 plus absolute value of z2. And another useful corollary is that the absolute value of z1 minus absolute value of z2 will be less than or equal to the absolute value of z1 minus z2. So I'm going to actually prove this statement. So the trick is to write z1 absolute value as the expression z1 minus z2 plus z2, and then apply the triangle inequality. So this will be less than or equal to the absolute value of z1 minus z2 plus the absolute value of z2. So we see that the absolute value of z1 minus the absolute value of z2 will be less than or equal to the absolute value of z1 minus z2. Now start with absolute value of z2 and do the same tricks. We see that the absolute value of z2 minus z1 plus absolute value of z2 is greater than or equal to absolute value of z2. So this implies that the absolute value of z2 minus the absolute value of z1 is less than or equal to the absolute value of z2 minus z1. But the absolute value of z2 minus z1 equals the absolute value of z1 minus z2. So we have that the negative of absolute value of z1 minus absolute value of z2 is also less than or equal to absolute value of z1 minus z2, and the result follows because we showed that the quantity z1 minus z2 and its negative are both less than or equal to the absolute value of z1 minus z2. And another quick corollary, if I replace z2 with minus z2, we get that the absolute value of z1 minus absolute value of z2 is going to be less than or equal to the absolute value of z1 plus z2. Again, we just get this by plugging in negative z2 in for z2 in the previous expression, and noting that the absolute value of negative z2 is equal to the absolute value of z2. So we'll end this lecture with a few visual examples of sets of points in the complex plane. So let's draw a sketch of the set of points determined by the relation first. Let's look at the relation real part of z plus 1 equals 0. So if I write z equal to x plus iy, then z plus 1 will be x plus 1 plus iy, and then the real part of z plus 1 will be the real part of x plus 1 plus iy, which is just x plus 1. So this is the line x plus 1 equals 0. If I set the real part of z plus 1 equal to 0, I get the line x plus 1 equals 0, which is equal to the vertical line x equals negative 1. So in the complex plane, this would be the set of all points that are have real part negative 1. So it would look like that. Next, let's look at the relation absolute value of z plus 2i is less than or equal to 1. So if I rewrite this as z minus negative 2i, if this expression was just equal to 1, this would be a circle centered at negative 2i and with radius 1. But since it's less than or equal to, this is a disk centered at negative 2i with radius r equal to 1. So this would look like negative 2i be on the imaginary axis. So here's the real axis and the imaginary axis. Then minus 2i would be right here on the negative imaginary axis. And so the circle centered at negative 2i with radius 1 would look like this. And since this is less than or equal to 1, I could shade in the whole disk. So this would be the set of points absolute value of z plus 2i is less than or equal to 1. finally, let's look at the set of points defined by the relation absolute value of z bar plus 3i equals 4. So this will be a circle, and so if I rearrange this expression, I can think of this, the absolute value of z plus 3i as the absolute value of z minus 3i conjugate, as the conjugate of z minus 3i. And then we know that the absolute value of a conjugate is the same as the absolute value of the complex number itself. So the absolute value of z minus 3i conjugate is equal to the absolute value of z minus 3i. And so we see that the absolute value of z minus 3i equals 4 is the circle centered at 3i with radius 4. One, two, three. Here's 3i. So the circle centered at 3i with radius 4 would look something like this.